We will study the absolute and gauge pressure today. Suppose you are having a container, and in this container any fluid is available. This fluid, whatever fluid is air there, maybe air or maybe any liquid. Suppose let's take the water. What you do, that somehow you make an arrangement that uh, prepare a lid, and somehow you suck whatever the liquid inside is in this one. Okay, and nothing is left in this one. Okay, so there will be a situation which will be created, and this situation is called to a vacuum. Okay, now at this time whatever the pressure inside will be is 0. The pressure inside at this moment will be 0. Okay, and what exactly is this pressure is called as zero absolute pressure. Zero absolute pressure. Okay, now any pressure you want to measure which is above the zero absolute pressure will be called as absolute pressure. Okay, so whatever is above that this pressure, whatever is above of this pressure, and you measure it, that will be called as absolute pressure. Okay, absolute pressure. Now, so what you can write is that P absolute. Now, uh, in our study, whatever study we will be doing, this absolute pressure is the standard atmospheric pressure. Okay, this is the standard atmospheric pressure. Standard okay, so what you can decide, we can write it as that your P absolute is your P atmospheric. Okay, so this is you can call this is a datum pressure. Above that you are measuring it. So if we talk about what the pressure we have to consider as a standard one or a reference one, so P atmospheric as a standard value, whatever is, I mean this value is 101.3 kPa, and this, please note it down that this temperature is at the 15 degree Celsius temperature. So if the temperature changes, this P atmospheric will also be changes. Now first thing is done, I mean second thing is done. Now any pressure you measure above or below, I mean because you have taken the reference as the atmospheric pressure, so any pressure you are measuring above or below the atmospheric pressure is will be called as gauge pressure. Okay, so any pressure above, okay, above or below you measure from the atmospheric pressure will be called as gauge pressure. Okay, that is your gauge pressure. Sorry. Okay, now so if we want to write it in form of the equation, what we can write is that P absolute will be P atm. Okay, is it, sorry, plus P gauge. So for the gauge pressure we are using the term Pg. Now using this equation, considering that P atmospheric is your standard pressure. Okay, standard atmospheric pressure, whatever pressure you above noted down, that will be P gauge. So let's take any quick example. Suppose at any location, if you are having, I mean, suppose this is a liquid, okay, and this is a container, and this is completely filled, and we are somehow managing a pressure where this value is coming out to be 300 kPa pressure, okay, and this 300 kPa pressure is your absolute pressure, okay. So if I ask you what will be the P gauge, then your P gauge will be P absolute minus P ATM. That will be 300 minus 101.3 kPa. Okay, this really comes out to be 198.7 kPa. So if we want to represent this whole concept in a graphical format, what we can assume that we just consider a line that is your P absolute, okay, and this P absolute, what we are considering is your 0, okay. Now whatever you are adding above this one, this is your pressure scale that will be happen at vacuum, okay, vacuum. Now if you draw a line, okay, and we talk about the what P absolute, okay, at any location, and first of all we figure out what is the P ATM, that is your P atmospheric pressure, and at this location your P gauge at this time, your P gauge will be 0, okay. And let's talk any point which is above this point or below this point. Here we can find out what is the P absolute, okay. So here the P absolute will definitely be lesser than this value, and here the P absolute will always be higher than this value. So if I talk about the how much pressure which is above this one is your P gauge, okay. So this value is positive, and if I talk about this one, that what exactly is the pressure gauge over here, this will be PG. So if I want to reach this point, this particular point, what you have to do, you figure out what is the P atmospheric and just subtract the P gauge, and if you want to note any pressure above than the P atmospheric, you just add the gauge pressure, then you will get the absolute pressure. Now what usually is that we are always aware that what will be our standard pressure. So throughout this course, what we will assume that pressure what we will be reporting throughout the course will be considered as a gauge pressure until unless it is stated otherwise. Now let's try to understand this particular concept, because this concept will be used throughout this particular course. So let's take an example, and this will be easy for you to understand, okay. So you are having a football, okay. In this football, what we are giving that our gauge pressure, it is given to you that P gauge is 100 kPa, okay. Now, and if it says that at this any location, the local atmospheric pressure, pressure that you can write P atmospheric is somehow 105 kPa, okay. In this situation, if you have to determine what will be the P absolute, what will the value of P absolute, we can determine from the concept I have just discussed above. So what exactly scenario, why I am mentioning that this is a local pressure, because if you go much away from the mean sea level at the locations which are at the high altitude, there may be situation where pressure will be much lesser than the P standard atmospheric pressure, but that value is 101.3. so in that situation the pressure might be like something like 99 or 100 kPa, and if you go much below that, this one deeper, this one, you may occur a P higher atmospheric pressure compared to the standard 101 value, okay. So this is your local pressure, okay. So let's figure it out what absolute pressure is. So this P absolute will be P atmospheric plus P gauge. So this value is 105 plus 100. This value will be coming out to be 205 kPa. Okay, that's your answer. Similarly, there are many permutations are very much possible. So using either, out for using this particular problem, what exactly scenario, always two things will be there, will be given to you, one will be unknown to you. Okay, so there are many permutations, three permutations are possible where you can figure out that either this one, either this one, either this one, when it is subjected to that two things are given to you. So there is no big deal for solving this problem. Okay, once you are able to understand the concept of this one. For the next task, we have to understand how the pressure varies in the static condition. Okay, so if you are having a container, so if I talk about the 1 point over here, 1 point over here, 1 point over here. Okay, so there are these 3 points are over there, such that this is just above this point, and these points are the two level, two different points at the same level. So how the pressure will be varying when one is moving in the same horizontal level, and how the pressure will be varying once one person is moving downwards. Okay, so we'll be doing this particular aspect in the two parts. This is your static pressure variation. Okay, so there are two cases, first case, second case. First case, when you are moving in the horizontal direction. Okay, and once you are moving in the vertical direction. Okay, so let's take the first example first. Okay, now, so in this particular liquid, if we take any, suppose there is this scenario is such that this is a container and this is completely filled up with water, and we are taking any element, okay, which is in horizontal action, such element. Okay, and let's try to understand. So just in order to understand how the pressure is varying, we have to figure out the free body diagram of this particular water element. Okay, now, so if we want to figure out what is the free body diagram, let's take any element. Okay, this element is such that I'm just intensely making it an inclined so that you can understand. So I'm taking any element which has a length of delta y. Okay, delta y, and such that its area is A, or you can say delta A. So on both sides this area will be delta A, and pressure on this side is your P, let's say P, and we are not aware that how much pressure will be here. So let's understand, let's take that this pressure is your P plus del P divided by del Y and multiplied by delta V. How this is coming into picture? Because this pressure, we are moving along the length of y, so this is the change in the pressure along the y, and how much length we have moved is delta y. So this is the change in the pressure that will be here. Now, in order to if particular this fluid element is in equilibrium, all the summation of the forces will be in this direction will be 0. So what we can write is that Fy is equal to 0. So let's figure out what is the forces. So this is P delta A minus bracket में P plus del P divided by del y multiplied by delta y multiplied by delta a, okay, that will be 0, because if you see summation of all the forces over here, so pressure here multiplied by the area, pressure here multiplied by the area, okay. So if you are going along this direction, this is positive and this is negative, so this equation will be coming out to be, okay. Now let's solve this equation. So if we solve with this equation, what we will notice that this delta a is common, okay. So delta a when cut out, and p, again this p will be cancelled out, okay. So what left is your delta p divided by delta y multiplied by delta y multiplied by, that's it, is equal to 0. So this is the multiplication of two things is coming to be 0. So either this will be 0 or this will be 0, okay. So if we look at this thing, delta y cannot be 0. Why this delta y cannot be 0? Because this is the length we have assumed, okay. So even if it is infinitesimally small, it has some length, so it cannot be 0, okay. The only left possibility is that delta p by delta y is 0. So if you consider this thing, what exactly it means, if you are moving along the y axis, the change in the pressure is 0, okay. So if we simplify this thing, we can quickly write that delta p is 0. So if we talk about the what is the physical significance of this thing, this says that the change in the pressure is 0, so the pressure remains constant in the horizontal plane, okay. So okay, similarly if you talk about this thing, because this is a container, we were moving in this direction and similarly into the plane, okay, because this is 3-dimensional. So in this direction, y direction, and which is x direction, okay. So similarly you will get the same equation, okay. So what we can write over here as a conclusion is that it will be good to note that pressure remains constant in the horizontal plane. Okay. So in other words, what you can say, additional requirement is that this will be only to hold when your force is in static equilibrium. That you have to remember. Okay. So two things are done, like you are moving in the horizontal direction, so here or here. Now we'll take the second case, when you are moving into the vertical directions, okay. So let's first of all draw the free body diagram for any fluid element what we are taking, okay. So let's do this thing. Now we are again taking a water element, okay, such that this has a very small length and this is having a length of delta z. Now what we are assuming that here your pressure is P, okay, and now what we are assuming is that here your pressure is P plus del P divided by del Z, and you have the length of the element is delta Z, so you have to multiply the delta Z, that will be giving you pressure. Now the area of this cross section is A, okay, so force at this location will be P multiplied by A, and similarly this pressure multiplied by A. Now there is additional one thing which is coming into the picture, that is the weight of the fluid element, okay, and this weight will be working from the CG, okay, and let's say what will be the weight of this one. You can quickly figure out whatever is the volume inside this one and multiplied by the density and then multiplied by the g. Or you can say that first of all figure out the volume of this fluid and then multiplied by the specific weight of the fluid you are considering. So let's say the specific weight of this thing is your gamma. So what will be the volume? Volume will be your area multiplied by the height of this element, which is delta z. So A delta z, that will be your volume, sorry, weight. Okay, now so let's write the equilibrium equation. So equilibrium equation will be that summation of all forces in this direction. So this is our z direction, so summation of all forces in this direction is 0. Okay, so the equation will be coming out to be there's one more thing I'm missing it. Okay, what we assume that the area is delta A, so let's stick to that particular thing. Again we can write over here that delta A, that will be easy to understand this thing. This is delta A, this is delta A, and this is delta A. This surface, what this area is your delta A. Okay, this area is delta A. Okay, now let's go for the equilibrium equation. So what we can write as equilibrium equation. So vertical force which is working is your P, and it is working on the area is delta A. Okay, now the additional forces which is against this one is pressure, that on the other face is P del P divided by del Z and multiplied by the delta Z, and this is working on the area delta A. Now there is additional weight of the fluid element, that is gamma multiplied by delta A delta Z, and if it is in equilibrium that will be 0. So if you solve this particular equation, this will be P delta A minus P delta A minus del P del Z delta Z delta A minus gamma delta A delta Z is equal to 0. So this will cancel out. Okay, the only thing left is this one. So if you quickly look at this one, again the delta Z will be removed, delta A will be removed. The only thing will be left is your minus times of del P divided by del Z is coming out to be this is gamma. So if you simplify more, you can write it that del P is equal to minus gamma times of del Z. So if you want to write in differential form, you can write it as dP is equal to minus gamma dZ. So if you talk about the physical significance of this one, is said that once you are moving in the vertical direction, okay, once you are moving in the vertical direction, pressure is getting decreases. So whatever the pressure was there, and this is the, and this value is whatever is coming out to be, this is the gradient. Okay, so del P divided by del Z is minus times of the specific gravity of the liquid. Okay, and that is called as the gradient of the pressure change gradient. Okay, so what we can figure it out that pressure will be decreasing, will decrease as one moves upwards in the fluid. Okay, so that's how this thing is concluded. Now there's one more important thing what is assumed has to, I mean what assumption is involved there, that for to hold this particular equation there is this thing that the liquid we are using is it has to be incompressible. Why we are saying this thing? Because what exactly will be there if it we have to, if we consider this it is in equilibrium, uh, this one, no. What scenario is involved is over there is that if you are taking this one, okay, so if I talk about this point and this point, so this point is subjected to a pressure, let's say all direction is P, okay, and the difference in the level of these 2 points is, let's say, H, okay, let's say H. So at the pressure at this location will be higher than the gamma H. So at this location pressure will be P plus gamma H. So whatever liquid is here is subjected to this much pressure, and whatever liquid is subjected to this pressure. So if pressure is changing, definitely density is going to be affected. If pressure is increasing, density will be higher at this location, okay, then your equation whatever you got over there, that will not be as simple as you have seen in the previous derivation. So in order to simplify this thing, what we are assuming that this will be incompressible, so that the change in the density with the depth we will be not be considering. And already we have seen that with long change in the, I mean long at the deeper depth of the sea, if we change the pressure and consider that fluid is compressible, so change in the percentage in the densities are hardly ranging from 2 to 4%. Okay, so that's all for the today's class.